Thank you, Professor Kapdi, for that very interesting presentation. We request you to engage to answer some of the audience queries, if possible. So, my first question has to do with the phosphorus centers that have been central point in this discussion so far. So, we'd like you to comment on the stability of these phosphorus centers towards oxidation because, as you know, phosphines in general, this has been a concern.
I think it's a very good question. I think a very relevant question when we are working with phosphines. One thing which we need to understand is when it comes to sigma donor phosphines, as what I've said, phosphorus having lone pair availability when it is much higher, the reactivity towards oxygen is also high. So, for example, tri-tertiary butyl phosphine can oxidize within seconds. And that is my experience when I was working with my PhD as well. This ligand, especially the PTBS of what we have shown here, if you see that the quaternary ammonium tries to reduce the electron density on the phosphorus. So the phosphorus is not a attacker. If you allow the phosphorus to oxidize, it takes much longer period for oxidation. In some cases, it might take even a week or so. The bigger challenge for this ligand is the moisture sensitivity because you have a sulfonate group. But oxidation, we have seen that it doesn't oxidize effectively because in water, when you are carrying the reaction, because you have dissolved water, oxygen as well, otherwise it should have been more oxidized to the phosphine oxide first and then coordinated with palladium. Even that chemistry is known, phosphine oxide palladium chemistry is known, but it doesn't do that. We have confirmed phosphorus palladium complex formation, and we have confirmed by ESIMS that it does effectively work as phosphine only. So you have to work with the electronics. We need to understand the electronics. But when it comes to sigma donors, it is very difficult. Even triphenyl phosphine, if you keep it on bench for a day or two, it doesn't readily oxidize. It's a very poor donor as such. That's the idea which you have to take for PTBS. It becomes a much lesser donor. In that case, it doesn't oxidize that effectively at all.
Thank you, Professor. As an additional question, for these aged phosphine ligands, are there specific guidances towards safe handling, and are they different from that of that which we normally read about, how to safely synthesize and handle phosphates?
They are very safe ligand. I can tell you when it comes to commercialization itself, our group has been synthesizing these ligands on gram scale, sometimes 30 to 40 gram or 100 grams. We simply store it under nitrogen. Till now, nothing has exploded. So I can assure you, nothing of that sort happens. Even when it handles with respect to the stability, there is no problem. Now, when it comes to its biological effects, unless until if you compare that with any other phosphine as an organic compound, it will have its own toxicity. But if you look at its stability as a molecule, it is pretty stable. So you don't need a different setup as such when you are either working with it, synthesizing it, or storing it. There is no problem. The only storage point which we always say is keep it away from moisture, and especially in Mumbai, moisture is very high, humidity is very high. So we store it under, like a jacketed system, or especially what are called as, under nitrogen, either in the Schlenk tube or in desiccators.
Thank you, Professor Kapdi. One of the audience members had a question that why not just resort to N-heterocyclic carbenes? Because that's a huge literature body out there, and it appears it might work for all of these reactions.
N-heterocyclic carbene chemistry, if you see, has been shown. I had shown one example of this. It is phosphine or it is N-heterocyclic carbene. So, for example, Michael Organ, he has done extensive amount of work where Pepsi ligand, Pepsi complex, which is an N-heterocyclic carbene coordinated palladium complex, that has been used for CCl activation. So the two mechanisms are different. What we see is heteroarenes, those catalysts were failing. And that's why we entered this area, and we have shown that as compared to N-nitrocyclic carbenes as well, where the activation of CCl bond is more important. That is a mechanism of oxidative addition that is generally happening with a metal which is electron rich. In such a case, when you have a heteroatom like pyridine or pyrimidines, they tend to then coordinate more effectively to these metals, and then the reaction doesn't proceed as effectively as what is expected. But if it's an aromatic halide, chloride, bromide, iodide, there is no match. N-nitrocyclic carbene, especially palladium PEPC and other complexes, are very effective.
Thank you, Professor. We have many students here on this call, and one of the points that came up is when we are looking at reproducibility of these results, they'd like to know in terms of experiments, how do we try and ensure the reproducibility? What is the methodology, the best methodology?
Is it like a general question they want to answer? Yeah. I will give you an example from what we do. So what we generally do is, if one student is working on chemistry like this, it is always reproduced by the colleague. The results are generally matched. If you see, there are collaborations that we have in various groups. So when the chemistry is being looked upon from other group as well, that chemistry is repeated in other groups, either in India or in Germany. We have also demonstrated this in a company, which means the company people are also able to reproduce this. Unless until this is done, and we are getting either reproducible results, which is isolated products, or we are getting better results, because sometimes the handling of professionals is definitely better than a first-year student. Then in that case, it is much easier for you to confidently go ahead and publish it. So we have a culture in the group that wherever a chemistry is going on, someone in the group is going to reproduce it. But in your case as well, I would suggest you that when you have done a reaction, maybe 5 or 10 reactions, and you're confident that the reaction is proceeding very well, a catalyst is working very well, go to your colleague, ask them to try the reaction again. Even if it doesn't come to that 5-10% margin error, that is good enough. If you get 80%, that person gets 70%, not a problem. But what it suggests that the conditions do work in different hands. That is very important when you are going to publish it, because anywhere around the world, industry-wise, academia-wise, if they feel that there is interest in this type of catalytic system, they are going to use it, they are going to reproduce it, and that's where some questions can arise. I can maybe give one small example here. The first generation catalyst which I showed, when I had submitted the paper, it had gone to JOC, and the referee was somewhere sitting in America. Now, I had no idea first. It was taking a lot of time for publication, but after that, when the reviews came in, after the publication was happened, it came outside. I got an email from one of the professor in America stating that we were trying to reproduce your chemistry. Once we see that the chemistry worked in our hands of synthesis of complex and the chemistry in our lab, then only we were able to confirm, and then it proceeded forward. So maybe I was not very sure whether they were trying to tell me that they were the referees, but it gave me an idea that yes, people do believe in reproducibility, and we should be happy if it does get reproduced in various parts of the world as
well. Sorry to interrupt, Professor Kapdi and Kaushik. Due to the paucity of time, we can take only one more question.
Thank you, Neha. So our final question for today, Professor Kapdi, is what drives the choice of metal that has been used with the PTABS? So in theory, can we use, for example, manganese? Or yes, are there limitations to what metals can work with this?
I think I would say it's the chemistry which will kind of define the role of the ligand. Metal should not be a problem, according to me. So if you're looking at the chemistry, you can always talk to us, because even switching from palladium to copper, we saw that there were similarities electronically as well. Switching from copper to rhodium, we saw the chemistry was defining it more, that somewhere the coordination was more important, solubilizing the rhodium in solution. So if you look at manganese or any other metal, even cobalt for that matter, people have asked me for this ligand, and I can assure you that there are people who are trying various metals at this moment. Ruthenium was also tried. I know that there is some results. So ruthenium has worked. I'm sure cobalt, manganese, or any other metal, because it's a ligand at the end of the day. Only thing is, what are you going to use for? Because it will not give you an electron-rich metal. It will reduce that electron richness to a certain extent, release that electron density back to the phosphorus. If that helps you in your chemistry, absolutely no problem. Want to do it in water? Absolutely no issues at all.
Thank you, Professor. So I'd like you to deliver any closing remarks to our audience today, if possible.
Yes, I think first of all, I have to thank again ACS, but for all of you, you're scientific enthusiasts, believe in your science. Anything which you start off with as young scientists, if you are a young career, if you are developing, if you have some ideas, do stick with that. It might be a small idea to start off with, but when it comes to a long-term period of science, do not worry what is the type of publication you get, whether it's a JAX or anything. That's just going to happen over a period of time. But believing in your science and trying to proliferate that science in the outside world, trying to get the feedback on your science is very important. That is something which we have done for the last 10 years. We have been doing it extensively in various places. Wherever there is an opportunity, we do that. But it gives you a lot of confidence, good suggestions come in. Even the questions which you asked today gives you a very good thought about what type of science you can do, how it can be applied. Please, 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 especially if you are in India, it's not just India. As such, generally, I would say, if you are a young scientist, you want to develop your career, do interact with companies. The real science works there. And if your science gets applied there, there is no, less satisfaction than to see the science going out in the world. So that's what I would say. Thank you.